All right, welcome back. I want to continue our conversation on IPv4 addressing. We saw previously that an IPv4 address needs a subnet mask, and that subnet mask is going to determine the network portion from the host portion. So the subnet mask is a contiguous set of 1 bits followed by all 0 bits. If we put where the ones end and zeros begin in our mask, we can see that in this example here, we have 24 1 bits, also known as the prefix length /24, but it identifies that the first 24 bits of our IPv4 address is part of the network, and the last 8 bits is the host portion. So we look up here and we can see, 192.168.1 is the network portion, and this device here is 100 or .100 on this network. Now, in our previous examples, our subnet masks were all 255s and then followed by 1 or more 0. Valid subnet masks, well, they're 8 bits, well, 32 bits, but in 4 8-bit octets. So as far as the 8 bits goes, we can have all zeros, 1 followed by all zeros, which is 128. 2 ones followed by zeros, 192, 3 ones, zeros, 224, 4 ones, 4 zeros, 240, and so on. So notice that we have either all zeros or all ones, but if we have a 1 that then changes to a 0, the rest are all zeros. These are the only valid decimal numbers you can have in a subnet mask. Matter of fact, your operating system will not allow you typically to put in any other value. Okay, so are these valid subnet masks? Let's take a look. This first one here, all ones followed by all zeros, looks good to me. How about this one? Well, we have 255s and zeros. We've seen those before, but we have ones followed by zeros, followed by ones again. Not going to work. How about this one? This looks good. All ones followed by all zeros. Oh, we got that subnet mask somewhere not on a natural octet boundary, but it's good. It's all good. How about this one here? Nope, we have some zeros followed by some ones and even another 0. How about this one here? What about that 223? Nope, that's not going to work. Ones followed by a 0 followed by more ones. Okay. How about this one here? Let's throw that in there. Yep, that's going to work. All ones followed by all zeros. All right, so I said a subnet mask does not always have to fall on a natural octet boundary. So if we have this IP address of a device up here and has this subnet mask, what network does it belong to? Okay, all we have to do is copy the network bits, put a line here where the ones end and zeros begin, copy the network bits, which would be these blue bits here, these first 20 bits. Okay, that's why it's a /20, and then all zeros in the host portion. Okay, so our network address would be actually 10.1.192.0. Okay, so that's the network address. We have 12 bits for the host portion, or 4,094 addresses we can assign to devices. So again, the subnet mask does not need to always fall on natural octet boundary. In most enterprise service provider networks, it's not going to. So let's put our line here. Here's our network address, okay, with all zeros in the host portion. Here's our subnet mask, our prefix length. Put a line where the ones end, zeros begin. Okay, let's look at our range of hosts. Okay, so the network portion in blue is not going to change. First host will be all zeros and a 1. Our last host, all ones and a 0. Broadcast, all 1 bits. Okay, 192. So if we look at the last 2 numbers, the first 2 numbers, 10, 1, that's not going to change, the first 16 bits. But it's this third octet that has half of its bits on the network side and half of its bits on the host side. So yeah, it's going to change. It's going to range anywhere from 192 to 207 because it contains both a network portion and a host portion. Okay, by the way that a device determines what network it belongs to, I mentioned this before, it does a bitwise AND operation. This is an AND gate here. If we use 0 for false and 1 for true, okay, and an AND gate, both input values have to be true for the output to be true. So if I said Rick Graziani teaches at Cabrillo College and Rick Graziani teaches at UC Santa Cruz, both of those parts of that is true. Both those inputs are true, so the output that is true. That would be a true statement. If I said Rick Graziani teaches at Cabrillo College and Rick Graziani drives a Ferrari, I'll tell you right now that one of those is not true. So the output would be false. Okay, as long as one of those things is false, the output is false. Okay, or a 0. Okay, well, we use those rules. Put them right there. Okay, so a false ANDed with anything. If false is part of that sentence, the whole thing's going to be false. We need them both to be true. So here's our network address. There it is in binary. There's our subnet mask. Notice we have all trues here in where the 1 bits are, and then all falses here. So the thing is as long as if we have a true in the mask, or I'm sorry, a true in the IP address, then it's going to be true. Okay, but if we have a false, it's going to be false. Okay, so let me just go through that real quick here. Let me go through the mask here, and we'll see the end result of all this. Try not to go too far here. There we go. Okay, so notice what this results in using all 1 bits in our mask and an bitwise AND operation. All we're doing is copying this part of the address down here. It's identical. If you're a 1, then I'm a 1. If you're a 1, then I'm a 1. If you're a false, I'm a false. Okay, that's all it's doing. Now, as far as here, we have all falses here. So I don't care what you are up here. You know what? You're going to be false. You're going to be all zeros. So that's why an AND gate is used. And that gives us the network. This is how a device determines what network it belongs to. Every device does that, has a IPv4 address and a subnet mask, does a bitwise AND operation, says, voila, that's the network I belong to. All right, so how do devices get IPv4 addresses? They can be assigned either statically or dynamically using DHCP v4 for IPv4. Static assignments, okay, those are usually for, well, not all printers. I have one printer that does at home here that has a static address. I have another one that receives it dynamically. But we typically use it for servers, routers, things like that. Okay, things that need to have a fixed IP address. Now, we don't tend to want to do that for all of our client devices. It's error-prone, time-consuming. We could have duplicate IPv4 addresses. Rick remembers a time when that was the case. But it's been a long time since those days. Okay, this is showing the same thing on my Mac OS. That's what I typically use manually right here. Okay, all right. Dynamic assignment. So Windows showing DHCP. This is what we typically use for all of our client devices. Okay. And it's going to receive it from a block of addresses called an address pool. So your router at home actually acts as a DHCP server and gives you a unique IPv4 address on your network. This is showing it from my Mac OS using DHCP. We can see that right up there. Okay, what's my network address, by the way? Let's see, 10.150.80.164. There's my subnet mask. Let's find where that ones end, zeros begin. Right there. So my network address is 10.150.80.0. Okay. All right. DHCP. So typically what happens when a device joins a network, wired or wirelessly, it sends out an Ethernet broadcast, says, who out there's a DHCP server? I need IPv4 addressing information. Your DHCP server, typically your router on your home network, will respond, give you an address from its pool. and also give you a subnet mask, default gateway IPv4 address, and an IPv4 address of a DNS server. Those three things are going to be the same for everybody. So, but what you're going to get is a unique IPv4 address, 101 in this case. The default gateway, DNS server, subnet mask, that'll be the same for everybody. Okay, so let's talk a little bit about that address that you usually get. 1990s, Rick remembers these days. But, this introduced the World Wide Web, and this is when the internet began to take off. PC had been available, you buy a personal computer for almost about 15 years at this point. But it really people started buying personal computers when the World Wide Web, the internet had been around, but this is when it became really popular. So everybody was getting on the internet. And the IETF, Internet Engineering Task Force, realized, hey, we're about ready to run out of IPv4 addresses. Okay, so we got to do something about this. So what it did is come up with some short-term solutions: network address translation, private IPv4 address space. I'll talk about both of those. Classless interdomain routing. All that means is, hey, we don't have to give a subnet mask that ends on a natural octet boundary. We can be more granular about the range of host addresses that we give out. The long-term solution, and it is finally coming to fruition, is IPv6. And you may not believe, Rick, but take a look at your mobile devices. Take a look at almost 50, right now I would say, as time of this recording, it's almost about 43% of internet traffic is IPv6. All right, but it's coming. Long time coming. Okay, private IPv4 addresses. Excuse me. Public IPv4 addresses. Let's talk about that first. These are addresses that are routable via the internet, meaning the internet routers will forward packets to these IP addresses. These are public type of servers that anybody can access, possibly have access to. At least these packets can get routed there from anywhere in the internet. Private addresses. This is used internally by homes, schools, and businesses of all sizes. Okay, also known as RFC 1918 addresses. These are the ranges of addresses that can be used. Now, what does that mean? This means anybody internally can use any of those range of addresses. Yes, you can have a network inside your house, 10.0.0/8, and have 16 million plus devices if you wish. Now, these addresses are not reachable via the internet. Matter of fact, if your ISP receives a packet with either a source IP address or a destination IP address that is private, it's gonna drop that packet. Destination, because it says, hey, these addresses could and do exist in thousands, maybe millions of places all over the world, the same address. As far as the source address, it's going to drop your packets to say, hey, we're not going to be able to get packets back to you because your source address is going to exist in many thousands, millions of places all over the world. Okay, so these are only good inside your internal network. So your router that is, we sometimes say, publicly facing router, it's facing the internet, it's connected to an internet service provider, typically has a public IPv4 address. Okay, I'm just using these as examples. These are public IPv4 addresses as well. Internally, these networks, whether it's a home, small business, a school, or a large business, are going to have private IPv4 addresses, and they can use any of them. Okay, notice that these two businesses are using the same. These two are using the same also. Okay, so the router the router that connects these networks to the public internet will translate it from the private address to a public address. So this is known as NAT, network address translation. Translates between, well, the way we use it is translates between a private IPv4 address and a public IPv4 address. So as this packet inside this network, this is the source IPv4 address, and this is a public destination IPv4 address. So this stays the same inside this network, but as soon as it reaches this router to go out to the internet, it gets translated by your local home router does this. Translates the destination IP, the source IP address to its public IP address. And as those packets come back to your public IP address, your home router will translate it back to the proper private IPv4 address. Okay, now this does hide your device, but it is not considered security. We kind of sometimes think it is. I won't get into that here, but NAT is not a security feature itself. Okay, but let's take a look here. So here I have 3 devices here: private IPv4 network address, different host addresses in that private network. As they're all going to the same Amazon server here, but that does not have to be the case. Notice when this packet is received by the router, it translates it to a single public IPv4 address. Now, it doesn't have to be one address, but it can be. Notice that all 3 of these devices with different private IPv4 addresses are all getting translated to the same public IP address, quad 1. One more. Different private IPv4 address, but when it hits the router before it goes out to the ISP, it's going to have the same source IP address. This is what has saved IPv4. Okay, that we can literally use a single public IPv4 address to represent thousands of private IPv4 addresses. Because when those packets come back in, the router actually says, "Oh, quad 1. Now I'm going to translate that one to this private address, 10.10.0.10. How about the same? Look at this, same public address, destination address, same one, but it knows, the router knows, no, this one is for 10.10.0.20. And how about this one? Same public IPv4 address, but the router knows, no, this one's for 10.10. I'm saying 10.10, aren't I? 10.00.30, excuse me. Okay, how does it know that? I won't get into that here, but it uses UDP and TCP port numbers, source destination port numbers, to do all this. So talk about this in my TCP, when I talk about TCP and UDP. It actually looks inside the packet and keeps track of that. I won't go through that here though. All right. By the way, in another YouTube playlist, I have a playlist that's about examining IP addressing. Let's look at this real quick here. It's a little Python program that I wrote, works on IPv4 and IPv6. It says, which version of IPv4 do you want to use? We'll say 4. Enter the URL. So we'll type in www.cisco.com. Company I do some work for many years. Very good company. All right. So let's see what it gives me here. Notice it has told me that this is my private IPv4 address. This is what it's being translated to. This is a public IPv4 address. Okay, so that's my private address, but it's being translated by my router to the public address. This is the address my router that it uses to connect to my ISP. All right, this is the DNS server that when I typed in this URL, it knows that this is the IP address of the server, public IPv4 address. Okay, something happens called a TCP three-way handshake. We won't worry about that. But let's take a look at the packet. When it's inside my network, here's my source IP address. But when it leaves my network, here's the source IP address. Here's the public destination IP address. As it leaves the server, it's leaving with its public IPv4 address. That won't change, but it's coming in with destination IPv4 address. This is what it leaves with the server, with this public destination IPv4 address. But when it hits my router, it's getting translated to this private IPv4 address, which was my source IPv4 address. All right. So yes, we could have the same, and we do. These private IPv4 addresses are used in millions of places all over the world. Okay. Again, your ISP will drop packet if the source or destination IPv4 address is a private IPv4 address. Okay, so what this means is actually has kind of broken a fundamental principle of the internet called the end-to-end principle, but it means that we cannot communicate with each other directly. Okay, we actually have to go, both of us connect to a public IPv4 address, and that's how we communicate with each other. So this is known as, the end-to-end principle. Also creates some delay. Okay. I will also say that it's, with IPv6, we don't have that problem. We don't use NAT for IPv6. Another video. Okay, so finding your private IPv4 address. First of all, just in Windows, you can do ipconfig. If you're like I am, using Mac or Linux, you can do ifconfig. But there's in Windows, there would be my private IPv4 address. I can see it's private because it starts with a 10. What's my public IPv4 address? If you type what's my IP, you'll get your public IPv4 address. Do it in Google. Now, sometimes at school, we're dual stack. We run IPv6. So you might have to type IPv4. If it doesn't show up in Google or whatever browser you're using, just click on one of the links and it will show you. Now, what is this address here? 207.62.184.20. That's my public address. My private address is being translated to this public address as it leaves our network. Okay. So the public address, that's the address that the router is translating it to. All right, I don't need to go over this too much. You can look at this, but this would be my private address translated to the public address. All right, so once again, our routers all have typically public IPv4 addresses. I will make a note that some ISPs are running out of public IPv4 addresses. They may translate your private address to another private address, and then they'll translate all their customers or many of their customers' private addresses that they use and translate it to a single public address. It's known as carrier grade NAT or NAT 444. Don't worry about that here, though. What I'm showing here is that all of these devices are getting the same private addresses. Okay, so they all get translated to their unique public address. Going out and coming in, they get translated back to their unique private addresses, at least unique within their network. All right, just really quick here, I want to mention that when we get a network address, we usually divide it into smaller networks. So for example, if I have a barrel of 100 apples, I can divide that into 10 baskets of 10 apples, or any number of even baskets I want to. And that's tend to what we do in large networks, any kind of enterprise network. So if we have this network here, 10.0.0.0/8, this mask, over 16 million hosts, we can make it one big network, Ethernet switches, but this makes it one large broadcast domain. That means an ARP request from any device is going to be seen by all other devices. I'm not going to get into subnetting here, but I do want to mention, okay, what we tend to do is divide our large network into smaller networks. So let me do that. I'm going to divide this into 5 smaller networks. We'll call this the 10.1.0.0 network. Notice the mask change. 255, 255. So now we're saying, hey, let's make this second octet here, second decimal number. Let's make that part of our network. And we'll make that this 10.1, this 10.2, this 10.3, this 10.4, all at the same mask. We extended the length of our mask, borrowed bits from the host to create these subnets, 10.5. All right. So now what we could have is actually 256 smaller networks with 65,000 plus hosts each. 256 net. We're using just 5. 1, 2, 3, 4, 5. That's what that using 5 means. Okay. All right. So we'll talk about subnetting and all that a little later, but I just wanted to introduce that to you here. Okay, let's talk a little bit about who actually assigns these public IPv4 addresses. It all begins with IANA, Internet Assigned Numbers Authority. Okay. And they're the primary holder of both IPv4 and IPv6 addresses. They then allocate addresses to the 5 regional internet registries, RIRs. You can see that they're each one in a different geographical location. So then they actually allocate then the regional internet registries to internet service providers, but also content providers or companies that want to get an address directly from a regional internet registry. I won't go into the whys and wherefores of those for right now, but IANA, they start out with almost all 4.29 billion apples networks. So they can't allocate the private IPv4 addresses. There's also some other reserved addresses for multicast and that we won't get into here. But what IANA does is that they take their large barrel of 4.29 billion apples and they divide it into baskets, usually baskets of /8. So notice this. So these are all of our different networks. Okay. Now, some of these are, like 254 and 255, those we don't allocate, they don't allocate, but just for the sake of example here, these are all the baskets. Boy, they have 256 baskets here, don't they, of 16 million apples each. What do? They give different baskets to these 5 regional internet registries. By the way, IANA has run out of IPv4 apples addresses. Okay, so, and you can look all this stuff up. Which regional internet registry received what /8? Okay, you can just look this stuff up. It's all out there. Very cool stuff. Okay, but let's take a look at the 207/8, the 207 basket. That went to Aaron, okay, the regional internet for Canada and United States. Okay, what did Aaron do with it? Well, they divided that basket. They gave the basket, they said, well, I got the 207 basket. I'm going to give the 207.62 basket /16, 65,000 plus apples to Scenic. Scenic is the ISP for the California K through 20, the entire school system within the state of California. That includes primary schools, high schools, county office of education, community college, state universities, University of California, and other. Just as an example here, they gave another 207 basket, the 207-100, to another ISP, Verizon. Now, what did Scenic do with their 207-62 basket? They gave them to different colleges. Shasta College got everything from 207-62, which belongs to Scenic. They got the 179 to 182 baskets, 4 baskets of 256 apples each. Okay, Cabrillo College got 207-62, that belonged to Scenics, but they got the 184 to 187 basket. Gavilan College got the 201 and 202 baskets. So you can see how these get allocated. All right. And you can there's different tools you can use. There's some different whois tools and things that you can see what address belongs to who. All right. But I said that Scenic got the 207-62 address. We can see that right here. Matter of fact, here's one of the tools I use that says it went to what was known at the time CSUNet, but it's known as Scenic today. There's Verizon. Okay. All right, Cabrillo College, we got the 184 to 187. And again, we can look this up. We can get, if I typed in 207-62 187.0 to this tool I'm using here, then it would tell me that this Cabrillo College has this address. Okay. Okay, so what this tells me is this. Okay, so I can actually see, yeah, 207-62 184.0 to 207-62 187 255. Anything in that range belongs to Cabrillo College. Okay, so when I type in, here's my private IPv4 address. When I do what's my IP address, See this 207.62.184.20? Can you tell? I was at Cabrillo College when I did this. Okay. This is how content delivery networks, websites, and things, they know they can actually use this information to determine where you are or what ISP or location. Anybody see my IPv4 packet would know at the time I'm at Cabrillo College. They may want to give me the weather for Aptos, California. All right. If I do it from my house, this is saying, oh, your ISP is Comcast, but it also tells me, where are you? Well, it's kind of giving me some bad information here, but I can also, most of the time, it'll tell me I was in Carmel, California, that area near Monterey, California. But anyway, all right, we can also use a whois tool. So this is for my Mac, putting in a public address. It tells me who has that. It was allocated by Aaron and it went to Comcast. Comcast is my ISP. Okay, and there's other tools that we can use as well. And just to wrap this up, once again, your computer typically 99.9% of the time, maybe a little more than that, but I do know places that they do not use NAT and they do allocate public IPv4 addresses to the end devices, like University of California does that at most places, including the other place I teach, UC Santa Cruz. But most common, we have a private IPv4 address internally. And then this is, let's say I'm at home. This gets then translated to this public IPv4 address that belongs to my router. Okay, actually belongs to Comcast. And that's so when packets are within my network, they have this source IP address here. But when they reach the router, it gets translated to the public IPv4 address that belongs just to me. Well, belongs to Comcast, but it's unique to my router. Comes in from some public address to my public address and gets translated back. All right, I hope you found this helpful. Look forward to talk to you in later videos. Thanks.